Good afternoon, respected sir. Today I, Rajdeep Biswas, along with my fellow group members Adarsh Prasad, Pritam Mandal, Jemeema Tabasum, Anushmita Ghosh, Aheli Chakraborty, Tiyasha Chatterjee, Sayam Dogra, and Dipshikha Paul are going to present on the topic of biomechanical properties of native and tissue engineered heart valve constructs. As we know, among the diseases which cause death, heart valve disease holds a significant position. Nearly 25,000 people die each year due to it. Though 2,90,000 patients go through valve replacement per year, it is speculated that this number would reach 8,50,000 by the year of 2050. Though heart valves can be treated, serious heart disease require valve transplantation. There are two types of artificial heart valves available, mechanical and bioprosthetic. But even artificial heart transplants also have some drawbacks. Number 1, they prevent somatic growth. Number 2, mechanical valves are prone to infection, inflammation, and thrombosis, while bioprosthetic valves cause calcification, which has a stiffening effect on valve cusps. However, tissue engineering offers immense potential to suitable valve replacement. Now, my fellow group members will take over the presentation.
Next up, we have physiological forces and biomechanics of heart valves. We know that the primary function of heart valves is enforcing and controlling the unidirectional flow of blood during the cardiac cycle. They are essentially considered as passive tissues that are guided by the inertial flow of blood. These heart valves function over a complex cyclic tensile shear flexural loading environment of tremendously high mechanical demand of 30 million times in a year. During each cardiac cycle, the heart pumps about 3 to 5 liters of blood through these valves each minute. This results in a high blood velocity of about 1.35 meter per second through the aortic valve and physiological transvascular pressures of 10 mm of mercury and 80 mm of mercury for the pulmonary and aortic valves respectively. On the table we see in this slide the transvascular pressures observed in humans and bovine valves are shown. While the accurate values of stress these valves experience is unknown, the estimate values are 10 to 80 dyne per centimeter square for shear stress on the aortic valves. Some studies show these values to reach 30 to 1500 dyne per centimeter square, where the higher values were related to disease conditions. The in vivo strain in the circumferential direction of the aortic valves has been calculated to be 10% and that in radial direction to be 40%, while that of the aortic root is 5% in both circumferential and longitudinal direction. The cusp extendability in radial and circumferential directions are ER ranging zero point 0.6 to zero point 0.8 and EC ranging zero point 0.2 to zero point 0.3, where ER and EC are the laryngean strain in radial and circumferential direction respectively. The diastolic pressure occurs towards the beginning of the cardiac cycle when the ventricles are filled with blood, while the systolic pressure occurs towards the end of cardiac cycle when the ventricles are contracting. The majority of stresses and strains occur in aortic valve leaflets in the diastolic cycle and during the early opening of the valves. Assuming that the valves get deformed by blood flow through combined axial stretching and bending, elementary beam mechanics were used and the total stresses calculated were found to be 50 kilopascal and 500 kilopascal in systole and diastole respectively. Other studies found it to be in the range of between 200 and 400 kilopascal. The elastic modulus in radial and circumferential directions during initial loading phases have been found to be in the range of 2 to 10 kilopascal and 20 to 100 kilopascal respectively, while in post nonlinear transition phase it is 1 to 2 megapascal and 8 to 12 megapascal in radial circumferential direction respectively. The ultimate tensile strength of the leaflets are 10 times higher compared to the in vivo maximum stresses ranging 2 to 4 megapascal. These values can be taken as guidelines for ranges of stresses and strains in designing TEHVs, that is, material to be used in fabrication of TEHV should have sufficient range of mechanical properties to function effectively at these ranges of stresses and deformations. Now, I will be handing over the presentation to a next member of our team.
So after a brief introduction given by one of my team members, I am here to present on the subtopics structure and composition of aortic and pulmonary heart valves, also the mechanical properties of native and tissue engineered heart valve constructs. So let's move on to the next slide and continue with the presentation. So the first subtopic says structure and composition of aortic and pulmonary heart valves. Human heart valves are exceptional structures. These tissue paper like skinny membranes are connected to the heart walls, which open and shut to manage the blood flow, causing the sound of the heartbeat. This flexing of the tissue happens continuously. The tissue withstands about 80 million beats a year or 5 to 6 million beats in a whole lifetime. Every beat is a tremendous show of flexibility and strength. So after a brief introduction, let's dive into the details of the valves. The heart has basically 4 valves. The bicuspid valve, also known as the mitral valve or the left atrioventricular valve, and the tricuspid valve, which is also known as the right atrioventricular valve, that controls the movement of the blood from the atria to the ventricles. Then comes the pulmonary valve and semilunar valve that controls the movement of the blood out of the ventricles. Moving on to the next slide. So in this slide we are going to discuss the 3 basic layers of the valves. The aortic and the pulmonary heart valves have quite similar structure, consisting of 3 semilunar leaflets. The cross-sectional structure of the leaflets consists of a structure that is thin, flexible and tri-layered, which can be broken into 3 sublayers, namely fibriosa, spongiosa and ventricularis. Out of the 3 layers, fibriosa is the thickest and is primarily composed of an extremely dense network of co-regulated collagen type 1 fibers, which are arranged longitudinally and to a lesser degree in the radial direction as well. This is the main layer which bears the load of the blood flow. The scleroprotein, also known as the elastin, present within the fibriosa, forms an extremely organized network of filaments stretching radially from the central region up to the attachment of the leaflet. The walls of those tubes contain dense elastin sheets that surround the collagen fiber bundles. During the loading of the valve, the elastin stores energy and releases it to the collagen throughout unloading, thus allowing the valve to come back to its resting position. The next layer is the spongiosa, which is a sandwiched layer between the 2 other layers. It consists of a hydrated glycosaminoglycans and proteoglycans. Also collagen and elastins are loosely arranged. This layer has high importance as it functions to decrease the stress on the leaflet during loading and unloading. It basically acts as a cushioning layer. The thinnest of the 3 layers is the ventricularis, which consists of elastin sheets and collagen fibers. It functions to reduce the huge radial strain over the valves in its fully open state. The valves are fully open in conditions of high blood flow. The stress-strain characteristics of the heart valves are determined by studying its layers. The elastin fibers, which are wavy in structure, provides maximum stretching, whereas straight fibers are much stiffer. The fibers mostly contain water as its basic component, that is about 60 to 70% water, and thus are considered for the viscous response of the tissues. Moving on to the next slide. Here in this slide we will be discussing few of the studies that were conducted on native heart valves, that is, the mechanical properties of native and tissue engineered heart valves constructs. Biomechanical characterization of human native heart valves are rare because of the restricted accessibility of fresh human heart valves. Only a few studies are conducted on the properties of human heart valves, whereas substantial range of studies is bestowed on properties of animal native heart valves like porcine and ovine heart valves. Some studies were conducted on both human and porcine heart valves. However, every one of those studies revolved around a particular mechanical properties. So now let's discuss few of the studies one by one. A test that was conducted on 9 aortic valves from healthy people as obtained from a decreased patients who had not suffered from artery heart valve malady. All of them were aged between 49 to 50. The tissue were kept on a 4 degrees Celsius and the test was conducted at a normal temperature within a time span of 24 hours of death. The main target of their investigation was correlation between the biomechanical properties of valve leaflets and collagen crosslinks of the heart. However, the tested mechanical properties included solely unaxial tensile tests. Another study was conducted which experimented on 11 healthy human body pulmonary and arterial valves of the heart from the donors between the age ranging from 20 to 50 years. In fact, they also targeted solely the unaxial tensile stress strain behavior. Another study was conducted which also reported the mechanical properties of the arterial heart valve, in which 5 heart valves, 1 from female who had poisoned death and 4 from males who had an accidental death, all of them were aged from 15 to 27 years. Similarly, alternative studies involving biomechanical properties of animal native heart valves and tissue engineered heart valves largely centered on the investigation of unaxial tensile mechanical properties. Thus, in further slides of the presentation, we mainly focus on the mechanical properties that are followed by alternative mechanical properties including flexural, fatigue and elastic properties. So may I now request my other team members to continue with the presentation. Thank you.
Now we're going to discuss about the mechanical properties of native and tissue engineered heart valve construct. Due to increasing number of heart valve diseases, there is an urgent clinical need for off-the-shelf tissue engineered heart valves. In animal studies so far, the implanted tissue engineered heart valves have failed to survive more than a few months after transplantation due to insufficient mechanism property. Therefore, the success of future heart valve tissue engineering approaches depends on the ability of the THV to mimic and maintain the functional and mechanical properties of the native heart valves. However, aside from some tensile quasi-elastic data and bending properties, detailed mechanical properties such as dynamic fatigue, creep behavior, and viscoelastic properties of heart valve are still poorly understood. The need for better understanding and more detailed characterization of mechanical properties of tissue engineered as well as native heart valve construct is thus evident. The relevant data on both native and tissue engineered heart valve construct have been compiled and analyzed to help in defining the target ranges for mechanical properties of THV construct, particularly for the aortic and pulmonary valves. Biomechanical characterization of human native heart valves are rare in literature due to laboratory. Few studies have investigated the properties of human heart valve, while a considerable number of studies have been presented on properties of animal native heart valves such as porcine and ovine heart valves. Many studies regarding the biomechanical properties of animal native heart valves and tissue engineered heart valves mostly focus on investigation of uniaxial tensile mechanical properties. Moving on to the next slide, we want to discuss about the uniaxial tensile properties. Uniaxial tensile testing is perhaps the most common process of measuring the mechanical properties of heart valves. The figure and the graph demonstrates a representative example of stress strain curve for soft tissues such as human heart valve leaflets. The tensile stress sigma is defined as sigma is equal to F by A, where F is the applied force and A is the area of cross section in the release date. The tensile strain epsilon is defined as epsilon is equal to del L by L naught, where del L is the change in the length of the specimen and L naught is its initial length. The elastic modulus, also known as Young's modulus, is defined by the ratio of stress and strain. The following graph shows that stress-strain behavior of soft biological tissues such as heart valve leaflet is highly nonlinear. The convention used in description of different mechanical properties of soft tissues from a tensile stress-strain curve is also shown in the graph. The tensile stress-strain curve can be split into a number of regions, that is linear, elastic, transition phase, collagen phase, rupture phase, etc. The main phases of the curve are low stress strain or pre-transition linear elastic phase, which can be linked to the straightening of the creamed fibers of collagen and elongation of the elastin fiber. The highly collinear transition phase that might be related to the transfer of force from elastin to the collagen fiber. A post-transition linear elastic region linked with elongation of elastic collagen. A significant difference between human heart valves and those of common animal models such as porcine, bovine and ovine valves is evident. The animal heart valves are much weaker compared to human heart valves. This is one of the reasons that xenograft valve transplants in human lack long-term durability. In the next slide, Anushmita will furthermore discuss about the other mechanical properties of native and tissue engineered heart valve construct.
Moving on, now we are going to talk about the uniaxial tensile properties of tissue engineered HV constructs. Despite the extensive research and tissue engineering of heart valves over the last few decades, there have been few studies in which complete heart valve constructs have been fabricated. The number of tissue engineered heart valve constructs that advance to animal studies is even more limited. Studies in which the mechanical properties of the TEHV constructs have been investigated include those of Dreisen et al. In 2007, Balguid et al. In 2007, Engelmer et al. In 2005 and 2006, and Solian et al. In 2000 and Herstrup et al. In 2000 as well. Dreisen et al. In 2007 used a biodegradable scaffold of polyglycolic acid PGA mesh with an outer coating of polyhydroxybutyrate P4HB to produce a TEHV leaflet. Scaffolds seeded with cells from human vena cephana magna were conditioned in a bioreactor with a diastolic pulse duplicator. The leaflets were characterized in vitro and were tested for uniaxial tensile properties along the circumference and radius. The observed properties were then introduced into a computational model to further analyze the mechanics of TEHV. Balguid et al. In 2007 also used non-woven PGA scaffolds coated with a thin P4HB and seeded them with human venous myofibroblast cells to obtain heart valve constructs. Fibrin was used as one of the cell carriers. One of the most important samples were cultured under static environment, while another group, after 5 days of static culturing, was subjected to dynamic training for 3 weeks at a frequency of 1 Hz. Uniaxial tensile tests were performed on all samples. The results showed that replicating the composition of the extracellular matrix in TEHV, such as mimicking the collagen content of the native heart valve, does not necessarily ensure sufficient mechanical properties. The longest implementation study of TEHV so far has been reported by Herstrup et al. In 2000, Shinoka et al. In 1996, and Sodian et al. In 2000 as well. The authors first constructed a single valve leaflet for replacement of pulmonary valve leaflet using PGA mesh scaffold and autologous cells from a sheep. The tissue-engineered valve was then implanted into the very same animal. The initial high stiffness of PGA, the poor mechanical properties and the lack of seminal growth of the implanted construct were observed as issues of concern. Hence, the authors in their subsequent work adopted polyhydroxyoctanoate PHO scaffolds. They seeded the implant scaffolds with autologous ovine carotid arterial cells and implanted them into 6 lamps. Echocardiography data analysis confirmed no stenosis or thrombosis for up to 20 weeks. However, the slow degradation of the PHO resulted in a prolonged bioabsorption turned out to be of concern. The authors next chose PGA mesh coated with a thin layer of P4HB for their scaffold. Since P4HB offers higher initial strength and flexibility due to its thermoelastic nature and shorter biodegradation time, the PGA P4HB composites offered a good combination of porosity and mechanical properties. The PGA P4HB autologous tissue engineered valves were reported to function in vivo for up to 5 months and resemble the heart valves' structure, mechanics, and matrix composition. The large number of studies report the uniaxial tensile properties of both native heart valves and TEHV constructs. However, as noted earlier, the static uniaxial tensile tests are too simplistic and do not represent the physiological loading conditions on heart valve leaflets in vivo. For better characterization, dynamic biaxial and flexural properties of leaflets are relevant. Thus, now we have to move on to our next topic, which is the biaxial properties. While there are substantial data in literature on the uniaxial tensile mechanical properties of heart valves, data on biaxial tensile mechanical properties, especially the ones which are time dependent, are still limited. The given figure shows the biaxial tensile stretch loading unloading data for a human Arctic valve. The leaflet responses in the circumferential and radial directions are clearly distinctive. Collagen architecture of Arctic and pulmonary valves in its initial state is organized in the circumferential direction of the leaflets. The collagen fibers lay down pattern that defines the response to biaxial tension. In the initial stages of the test, the collagen fibers are stretching circumferentially and exhibit a rapid rise in the tensile stress with a minor increase in strain. The leaflet response in the radial direction takes place in 2 stages. The first stage, a toe region exists where a small change in tensile stress causes a large deformation. In the second stage, the tensile stress rises steeply until the tissue attains its ultimate extensibility. The toe region is the initial stage can be explained by the fact that valvular leaflets do not have many aligned fibers along their radial direction. The high compliance of the leaflet along its radial direction in the first stage of the tensile test allows leaflets to be stretched in the diastolic cycle, while the circumferential stiffness is important for supporting the high transvalvular pressure. Such anisotropic properties of the valve leaflets are important for proper valve functioning. The most commonly used biaxial tensile tests of the valve leaflets were described in detail in the papers of Greisel et al. It was recommended that during this test, specimens should be immersed in PBS solution at physiological temperature. The time-dependent response of heart valve constructs is of special interest. Stella and colleagues studied biaxial time-dependent tensile behavior of porcine Arctic valve leaflets. Their study included creep, strain rate, and stress relaxation under planar biaxial stretch from 0 to 60 Newton per meter. The tension versus stress relation was found to be insensitive to the strain rate, while a low level of hysteresis and significantly high level of stress relaxation were observed. The exhibited creep was negligible over 3 hours. These results contradicted the earlier findings on ligaments and pericardium, all of which exhibited significant creep. This indicates that the relaxation and creep mechanism in the heart valves are not dependent on each other. Sachs et al. In 2009 developed a series of tests that enabled microstructural insights into the mentioned phenomenon. By applying small angle X-ray scattering, the author probed the dependence of mechanical properties of the tissues on the kinematics of the collagen fibers under biaxial stress. In creep tests carried out for 60 minutes, both the tissue strain and febrile deep period strain remained constant. In case of stress relaxation, the febrile deep period strain decreased rapidly in the first 10 minutes of the 90 minutes test of deformation. The authors concluded that stress relaxation can be due to an internal slipping mechanism probably regulated by non-collagenous components such as proteoglycans, whereas the lack of creep in presence of stress relaxation suggested that no internal slipping was present under constant loads. Now I would like to hand over the presentation to my next group member.
flexural or bending properties. But before that, let us see what is flexural strength. Flexural strength, also known as modulus of rupture or bend strength or transverse rupture strength, is a material property defined as the stress in a material just before it yields in a flexure test. The transverse bending test is most frequently employed, in which a specimen having either a circular or rectangular cross-section is bent until fracture or yielding using a three-point flexural test technique. The flexural strength represents the highest stress experienced within the material at its moment of yield. It is measured in terms of stress. Now let us come to flexure or bending. It is a major deformation mode for heart valve leaflets. All the uniaxial and biaxial tensile experiments conducted on excised strips of valve leaflets dominate documented studies. These tests do not fully represent the physiological deformation of the valves. The actual physiological deformation of heart valves is largely a flexural deformation. An added advantage of using flexural tests is the fact that they allow for the quantification of strains at comparatively low stresses. Flexural tests were first conducted on heart valve leaflets in the late 1980s by Wesley and Bonner, when the calcification of glutaraldehyde fixed porcine prosthetic valves was attributed to flexural stresses, turning the bending properties of leaflets into a clinically relevant topic. The first flexural experiment employed a modified form of the three-point bending test method in which the leaflet strips were positioned vertically between two clamps that preloaded the tissue to a flattened state. By rotating the top clamp by 90 degrees, the tissue strip was bent over a mandrel. The bending moment and flexural stiffness of the tissue were then calculated using simple beam theory. The authors observed that the bending stiffness, Sn, increased with the tensile stress applied by the upper clamp according to the second order polynomial reaction given by Sn equal to 100 plus 2.1 sigma plus 0.083 sigma square, where Sn is the bending stiffness in NNM square unit and sigma is the applied stress in kilopascal or kPa. They also reported that the bending stiffness was only slightly affected by the preload applied to the tissue. Furthermore, it was observed that the neutral fibers of the deformed tissue were not located in the central plane of the cross-section, but closer to the side of the fibrosa. Since a located neutral plane is a prerequisite for the application of simple beam theory, the author suggested that this theory did not apply to their experimental setup. The flexural test experiments performed on heart valve leaflets can largely be classified into three categories: three-point bending tests, cantilever bending tests, and macro indentation tests. Three-point bending. A considerable volume of work on three-point bending properties of aortic valve leaflets has been reported by Sachs. One example is the work conducted by Gloeckner in the year 1999, in which the authors investigated the effects of fatigue on aortic valve bending properties. The bending stiffness EI was obtained using the linear beam theory according to the formula EI equal to FL cubed by 48 Y max, where F is the applied force, L is the span length between the two supports, and Y max is the maximum depth of indentation. The authors reported the experimental results in terms of a bending stiffness index (BSI) meant to serve as a basis for comparison of bending stiffness among samples. A mean BSI of 4.0 into 10 to the power 4 nm square was obtained in the circumferential direction, while a 4 times lower mean BSI was obtained in the radial direction, both for bending along the physiological direction of curvature. The BSI value almost doubled for bending against curvature in the circumferential direction, while no significant difference was noticed in the radial direction. In terms of fatigue, the decrease of the BSI for up to 200 million loading cycles was quantified. The results will be discussed in the fatigue properties section later. The observed differences in the non-fatigued BSI value were attributed to the complex structure of the valve tissue. The preferential orientation of the collagen fibers along the circumferential direction was responsible for the higher BSI in this direction. Also, when bending the leaflet against the natural curvature direction, the fibrosa was stretched and the ventricularis was compressed, opposed to the bending in the curvature direction in which fibrosa is compressed and ventricularis is stretched. Being thicker and composed of primarily dense collagen fibers, the fibrosa contributes the most to circumferential bending properties and thus increases bending stiffness in the adverse direction. Based on Gleitner's method, Engelmeyer developed a bioreactor specifically designed to subject TEHV to cycle unidirectional or two-way flexure and included an evaluation of scaffold bending stiffness for dynamic culture periods of up to 5 weeks. For determining the effective stiffness of the tissue constructs, they introduced a method based on visual monitoring of markers which represented the deformation of the samples. From these, they calculated the applied moment m and the change in curvature del k, which were plotted against each other. Through regression, a linear relationship was determined between the two, and finally the effective stiffness was obtained from the slope of this linear curve using the Bernoulli-Euler moment curvature relationship, m equal to EFI del k. The slope EFI is the flexural rigidity of the sample, the EF being the effective stiffness and I the second moment of inertia. Dividing the slope by I yields the effective stiffness value of the sample. By using the change in curvature, the authors effectively worked around the problem that the tissue was knocked out over supporting beams in a conventional three-point bending setup. The incubation of non-woven polymeric mesh scaffolds under dynamic flexure conditions led to a substantial decrease in effective stiffness for these scaffolds, while the loss of stiffness was significantly less severe for statically cultured scaffolds. In a follow-up study, the scaffolds were seeded with ovine smooth muscle cells (SMC), which led to increased stiffness after 3 weeks of culture, as the cellular component could contribute to the overall scaffold stiffness. It could also be shown that the flexing of the scaffolds during incubation led to a 63% increase in developed collagen compared to the static group. Using the same three-point bending method, Merriman investigated the effect of aortic valve interstitial cell in the year 2006 contraction on the flexural stiffness. They performed the bending test on valve leaflets after eliciting a cellular contraction and after inhibiting cellular contraction. Effective stiffness values of 150 to 200 kilopascal were reported, with an overall independence of stiffness from bending direction and flexural angle. It was also found that the mechanical contribution of the AVIC to the bending stiffness was largely negligible. Furthermore, the three-point bending test method first developed by Gleitner has been used for the evaluation of porcine heart valve prosthetics as well as pericardial porcine heterografts for valve leaflets. I would like my fellow group members to continue further with the presentation.
As my team member already explained briefly about flexural properties, now I will continue about the three different testing methods for flexural properties of aortic heart valve tissue, and they are three-point bending, cantilever bending, and macro indentation. Aheli already explained about the three-point bending. Now I will continue with the next two testing method, that is cantilever bending and macro indentation. Cantilever bending. This kind of bending is a physiological relevant to the local deformation. The valve tissue remains connected to aortic root and it is also in contact with other leaflets. Its attachment to the aortic root may be abstracted to the fixed end. Minazaffi adapted Glockener's device for cantilever bending test. The E effective of the belly region was about one-third of the valve. Contradictory to earlier results for bending of the belly region, the stiffness in the region was found to be sensitive to the direction of bending, and it was roughly 50% stiffer when bent against the physiological direction. Macro indentation. Macroindentation tests for aortic bulb tissue which were reported by Narin, who also investigated the effects of cryopreservation. Here, in microindentation test, the valve tissue is claimed over a round opening and it is indented within a ball probe, which results in a load versus depth of indentation curve. The main difference with respect to three-point bending is that the flexural response of the entire leaflet is tested, as opposed to cut out strips, and its direction is also dependent on the direction in which they are cut. Finally, it was obtained that load indentation curve determines the stress-strain equivalent. From the depth of indentation, the contact surface are between ball probe and leaflet were calculated geometrically, which was also used to convert the measured load to stress. Likewise, the strain was also obtained by comparing the contact surface area between ball probe and leaflet. Narin not only investigated about the ultimate properties of the valve leaflets, he also reported on stress and strain at a break. These methods of flexural test provides us complementary insight about the performance of tissue engineered heart valves, which constructs and this test in a combination are useful in understanding of the flexural properties of tissue engineered heart valves. These methods also have strong potential in the study of heart valve mechanics. Now, I request my team members to continue with the presentation.
Now we'll talk about another significant topic, that is the viscoelastic properties of heart valves. But before that, let's learn about what is viscoelasticity. Viscoelasticity is a property of materials that exhibit both viscous and elastic characteristics when undergoing deformation. Viscous materials like water resist shear flow and strain linearly with time when a stress is applied. Elastic materials strain when stretched and immediately return to their original state once the stress is removed. Viscoelastic materials have elements of both of these properties and as such exhibit time-dependent strain, whereas elasticity is usually the result of a bond stretching along the crystallographic planes in an ordered solid. Now let's talk about the effects of temperature on viscoelastic behaviors. The secondary bonds of a polymer constantly break and reform due to thermal motion because thermal motion is one factor contributing to the deformation of polymers. Viscoelastic properties change with increasing or decreasing temperature. Generally speaking, an increase in temperature correlates to the logarithmic decrease in time required to impart equal strain under a constant stress. In other words, it takes less work to stretch a viscoelastic material an equal distance at a higher temperature than it does at a lower temperature. So, let's talk about the types of viscoelasticity. Linear viscoelasticity is when the function is separable in both creep response and load. All linear viscoelastic models can be represented by a Volterra equation connecting stress and strain. Non-linear viscoelasticity is when the function is not separable. It usually happens when the deformations are large or if the material changes its properties under deformations. And anelastic material is a special case of a viscoelastic material which will fully recover to its original state on the removal of load. Now let's talk about the actual viscoelastic properties of heart valves. Viscoelastic behavior has been demonstrated to different degrees in native and pericardial based heart valve tissues, which are usually made up of highly organized ECM and valve interstitial cells. Though direct comparisons cannot be made between studies with different testing methods, viscoelastic characteristics including strain rate dependence, stress relaxation, and creep have been observed after loading of valvular tissue from ex vivo mechanical testing. Similar to arterial tissue discussed above, interestingly, mechanisms of stress relaxation appear to be distinct from those of creep. For example, stress relaxation observed in valvular tissue was accompanied by negligible creep over a 3-hour time frame. Therefore, use of multiple modalities for valve tissue viscoelastic property measurement is recommended. Now, handing over the slides to Pritam to continue with the presentation.
My fellow teammates have already discussed many of the mechanical properties of native and tissue-engineered heart valve constructs. Now I am going to speak about the fatigue properties of heart valves. Mechanical fatigue is an important part in heart valve mechanics. Failure of the valve leaflets may occur due to calcification and delamination of the layered leaflet structure due to the continuous repetitive cyclic stress from the complex combination of stretching, flexure, and shear. In order to understand the effects of fatigue on valves and TEHV or tissue engineered heart valve constructs, accelerated durability tests can also be used to induce fatigue in them. Not much data is available on this fatigue behavior of heart valves. The only data found on the fatigue behavior of heart valves is that of the effects of mechanical fatigue on 3-point bending properties of porcine bioprosthetic heart valves. These valves were fatigued to 0, 50, 100 and 200 million cycles of flexural stress with and against the curvature direction of the valve leaflets. In this, linear beam theory was also applied. The studies revealed that with the increase in number of cycles, the bending stiffness of the valve leaflets decreased significantly in both the radial and circumferential directions. When compared with a valve which had not been exposed to flexural stress, the decrease in bending stiffness index against the curvature direction was largest after 200 million cycles, around 80% less. The implantable TEHV constructs must be designed keeping in mind about this bending stiffness and other mechanical properties that deteriorate over time after implantation. In future, more importance must be given to the in vitro characterization of the effect of fatigue on important mechanical properties of TEHV constructs prior to investigation of in vivo performance in animals in order to reduce the costs and increase the chance of success in achieving the goal of an implantable TEHV construct. Now, what you see on the screen is a representation of the effect of fatigue on bending stiffness of heart valves. Now we will talk about the computational models of heart valve mechanics. In order to understand the mechanics of healthy and diseased heart valves, several computational models have been developed along with functional models of heart valves. Multiscale models which can seamlessly span and link the scales of cells, tissues and organs and ultimately molecular scales are necessary for understanding the disease mechanism of heart valves. The first step in this direction was taken by developing multiscale models for calcification-driven aortic stenosis of both the tricuspid and bicuspid valves. The bicuspid valves suffer from the calcific aortic stenosis more often than the tricuspid valves. Normally in healthy valves, the cusps are thin and pliable. Aortic valve generally consists of 3 cusps, with an exception of 2 in some patients, and surrounding tissues. Now in CAS or calcific aortic stenosis, calcified nodes may spread all over the cusps. By implementing multiscale models of aortic valve, Weinberg isolated the effect of individual parameters on the mechanics of valves at different scales. The bicuspid and tricuspid valves were remodeled, making them dynamic, 3D, and they considered detailed constitutive behavior. The simulations showed the expected organ level difference between the bicuspid and tricuspid valves. Now from the higher flexure in solid state and stronger jet formation in the fluid state of the bicuspid valve compared to the tricuspid valve, it can be inferred that the higher rate of calcification in bicuspid valves compared to tricuspid valves are not merely due to geometric differences. Researchers have designed specific hemodynamic environment such as waveforms of shear stress for valve surfaces to perform more illustrative studies. Cells experiencing the shear waves of the ventricle side exhibited an anti-inflammatory endothelial cell phenotype as opposed to the aortic counterpart. This result clearly shows how important computational modeling can be in understanding the mechanics of healthy and diseased heart valves. In addition, simulation results from these models can also help in achieving optimum design of TEHV constructs or tissue engineered heart valve constructs through iterative studies of structure to mechanical properties relationship for different materials. Now my teammate Tiyasha will take over the.
Now let's conclude the presentation with summary and future directions. Once the critical design criteria and required ranges for various static and dynamic mechanical properties of heart valves are established, designing suitable biomaterials and tissue engineering methods for achieving the desired ranges of properties will be necessary. An overview of common approaches used for tissue engineering of heart valves is depicted from various natural or synthetic biomaterials are seeded with various cell types such as endothelial progenitor cells, VECs, smooth muscle cells, adipose derived stem cells, and so on. Thank you, sir, on behalf of all my teammates for letting us this opportunity to work on such an informative topic.